Good morning. Thank you all so much for joining us. I am Garrett Bird. I'm a software engineer here at Fluid Numerics, and I also want to give a quick shout out to Dr. Joe Schoonover, the founder of Fluid Numerics, who helped me out a ton with the preparation for this talk. So before we get into things, there's a little bit of housekeeping that I want to take care of. So you can feel free to introduce yourself, ask questions, engage with the content or other people using the chat feature, which should be on the right side of your screen. At the end of the talk, we'll also have a question and answer, so Q&A at the very end. So you can submit questions anonymously through the question portal, which you can access by toggling over to the questions tab below your presentation window. And you can post questions through the chat, and we'll do our best to get to those at the end as well. And finally, this will be a recorded webinar, and so it'll be available on demand. And so you all should receive a link at the conclusion of today's events. And other small things, quick disclaimer, I am human, and so if I make any typos or I express any opinions that is not necessarily reflective of AMD. We are quite experimental here at Fluid Numerics. We're research focused, and part of that is believing that half of what we know today might be incorrect tomorrow. So, with that understood, let's get into things. So, there are a lot of initialisms here when dealing with this space between ML, DL, AI, and LLM. It's a little bit confusing. So, we're going to motivate this with the simple question: what is an LLM? And very simply, an LLM is a large language model, which is just a natural language processing model. It's the latest iteration that's just using neural networks, machine learning, and as we'll get into, a type of model called the transformer model to do language processing tasks. And this is usually in the form of some type of generative output. So text in, text out, but it's also broad enough to cover things such as dealing with like images, audio, even video these days, which is really exciting. So perhaps maybe from a bit more of a mathematical standpoint, we can think of it as a model that probabilistically predicts a sequence of words based on training data. And so maybe if you're on the West Coast and you haven't had your coffee yet, an even simpler way to think about things is that an LLM is just a robot you can have a conversation with. That will be a perfectly fine description for what we're doing today. And of course, there are a few vocabulary words that are floating around that you may have heard of. So we're going to try and define a few of these things. First up, we're going to define what a token is. And all a token is it's just a set of characters. It's just a string. It's really handy to just think of tokens as whole words because humans like to think in whole words. But in practice, it might be punctuation marks or chunks of words, perhaps like an ed or an ing ending. And there are even some tokenizer specific symbols that we'll see here. And so here are some tokens that I've actually generated, sampled from the Llama3 So we can see some full English words here, such as execute and film, but there are also chunks, not necessarily chunks, but other words with these sort of interesting sort of variations, such as message with this message and lifetime with the underscore prepending them, and get class, or not get class, but deposit and website with this G dot prepending it. There are also some words that are definitely not in the English language, such as the three in the top left here. These could possibly be from another language. Llama3 is multilingual, so perhaps that's further from. I honestly don't know. And of course, we also have, for example, some punctuation. And if we look in the very bottom right, this is an example of a tokenizer specific symbol that is used as a token, and that is actually the end of sequence token. So when we think about these models predicting what to say next, if it's generating it word by word, when to shut up is actually, it can be thought of as a word as well. So it needs to know when to stop generating stuff, otherwise it'll ramble on, and we'll actually see some consequences related to that later on. Um, but we can think of the end of sequence token as it knowing when to stop generating. So it's interesting that that in itself is a token. So, of course, tokens are chunks of strings, but as we all know, GPUs are not doing operations on strings all the time. They're doing operations on vectors and matrices and tensors and these sort of well-defined mathematical structures. So it's nice to know what an embedding is. So put very, very simply, an embedding is just the vector representation of a token. And exactly how many rows are in this vector depends on the particular model. You may have heard, for example, Llama 3 has an 8 billion parameter variant and a 70 billion parameter variant. And one factor that influences that number of parameters is how many rows are in an embedding vector for a given token. And we can actually think about this space of token embeddings as having a certain sort of dimensionality to it. So the classical example is that you might have the word man and the word woman. They would have a particular embedding, so a particular vector representation with floating point numbers. And if you take the difference vector between the embedding of man and the embedding of woman, this is the classical example. It tends to be very similar to the difference vector between the embedding of king and the embedding of queen. And that may not be particularly true for Llama 3, but in these types of models, it does tend to be true, and it illustrates the idea of this sort of hidden dimensionality and this hidden meaning that can be derived from embeddings. And these embeddings are gained through the training process, which we're not going to be speaking about today. Another important thing, so if, of course, we're doing linear algebra with these, uh, uh, we're doing linear algebra, right? So one of the most critical sort of elements is putting all these embedding vectors uh, into one form that we can sort of reference. And so one of the most important key components in these types of models is the embedding matrix, which is a matrix whose columns are each of these embedding vectors for every token in the model. So Llama 3, for example, has about 128,000 tokens in its library. So one side of that matrix is going to be at least 128,000 rows or columns long, and then the other dimension is usually on the scale of tens of thousands. So these are huge matrix and vector operations going on. And so that's just a little bit of what's going on under the hood. Of course, now we're using this advanced transformer model. This figure on the right was taken from the famous paper, Attention is All You Need. If you've been in this space at all, you've most likely either read this paper or at least heard of it. I think the last time I checked, it had something like 125,000 citations. So it's one of these really foundational papers that is really important to the space. So a little bit of high level understanding of what's actually going on in a transformer model is on the right. We can see in the lower left, we have our input, which for us is just going to be a prompt, so a chunk of text. And so that is fed in and it is encoded, and we'll briefly discuss what encoding does. And then it is more or less just considered with the pre-trained data, the weights and parameters of this model. And then some under the hood, more traditional machine learning operations are going on with neural networks and that type of those type of machinery. And then it is decoded, and then we actually end up with a vector at the end. We'll get on discuss a few different techniques as to how the output is actually found. But so traditionally what happens at the end, before any sort of like further filtering is applied, is we end up with a vector who has as many rows as there are tokens in the model, and each value in one of those rows would correspond to one of the tokens in the model, and those values are relative likelihoods, um, which is not necessarily a probability distribution. So in this Beatles example, right, we might end up with a vector who has, if our model just has these 5 tokens with these 5 names, then Paul might have a value, that likelihood vector for the corresponding value for Paul might have a value of something like 1,000, and then John and George might have a value of something around like 100 or something, and then we might even have negative floating point values in there if you're using floating point precision. And then this is converted using the softmax function to actually turn it into a probability distribution, and we'll define that later when we get into things such as start discussing temperature. And I've sort of glossed over it, but what the encoding process does is you can think of it on a high level as considering the position of words, either in an input or in context to each other as the model understands them. So if I say the sentence, Joe baked some chicken for dinner, that has a wildly different meaning than some chicken baked Joe for dinner. So of course, position matters very, very much in language. So the encoding process deals with position, among some other things. There are many, many layers that I'm glossing over here, but for the sake of a high-level understanding, that this is perfectly sufficient for what we'll be doing today. So that's a little bit of what's going on under the hood. It's fine to talk about theory all day, but of course, at some point we need to define what do I actually need in terms of hardware, operating system, software. So let's go through all of that. So of course, you'll need a ROCm compatible AMD GPU. Today we'll mainly be looking at an AMD Instinct MI210, which is of course from the Instinct line. AMD has these wonderful compatibility matrices in their documentation. As you can see, the tabs at the top, they also give compatibility matrices for the Radeon Pro line and the Radeon lines. So first checkbox is to have an a ROCm supported GPU. And then of course you need a ROCm supported Linux distribution. So today we'll be using Ubuntu Jammy or 22.04.3. And an important thing to note in terms of the support matrices, supported simply means that that hardware or that operating system is tested and it is verified to work. So if a piece of hardware or an operating system is unsupported, it very well might still work with the ROCm ecosystem. I can say anecdotally that on my personal machine at home, I'm running a Radeon 7600 XT on Arch Linux, and that is not a ROCm supported GPU, and that is not a ROCm supported operating system, but I have had wonderful, wonderful success running very similar types of models on my home system. So that's a bit of the lower level stuff. What do I actually need to install in terms of tangible software, right? Of course, we'll need to install ROCm, and today we'll be using ROCm 6. Conda, of course, when we're using Python, is almost a necessity. Today we'll be using Miniconda, but you're more than welcome to use the full version of Anaconda. We'll need a tensor framework. Today we'll be using PyTorch. We will also be using the wonderful, wonderful Transformers library, developed and provided by Hugging Face, and there will be a few other things along the way, such as pip and Jupyter, that we'll discuss. So installing ROCm is very, very easy. AMD provides some very nice documentation for the installation process. They go into a bit more detail in the documentation, obviously, but you can find these commands provided in there. And for example, this is the Ubuntu installation for the latest version of ROCm. So super easy, right? Copy and paste and run this, and you should be on your way to installing it. It is super easy, and I believe they also provide similar commands for the other supported operating systems in that documentation. So, first checkbox is to install Rockham. Next, of course, is to install Conda. It's the same story. The documentation is quite nice, and it provides uh, just a handful of lines, right? Even fewer. So super simple to install Conda. Um, so that's that. And then this is where things get a little bit messier. So we'll start off with a little bit of boilerplate, just creating a Conda environment, activating it. Of course, we need to install pip, and we will use pip to install Jupyter Lab because who does not love Jupyter notebooks? Next up, we will install PyTorch into this environment. Now, this is a little bit scary of a command to install PyTorch, but actually on the next slide, we'll see that the PyTorch documentation is also super nice, and it is very easy to get exactly what you need in terms of an install command. So we'll be installing transformers. The accelerate library is sort of a complementary library that's also provided by Hugging Face. We'll mention later on when we actually get our hands on some code where the accelerate library comes in. It tends to just make things a little bit easier. And the weird one out of this bunch is Git LFS, which stands for Git Large File Storage. Of course, these models tend to be pretty large, at least on the scale of multiple gigabytes. So Git Large File Storage tends to also sort of grease the wheels in that process when we get clone to download these models. And here's a screenshot from PyTorch's documentation. They have this lovely GUI installation matrix where you can choose your build of PyTorch, your operating system, what your package manager is, and what your compute platform is. And it will spit out on the bottom exactly what you need to run to install that version of PyTorch. It is very handy, very easy to use. So at this point, right, we have all this stuff installed. We have the hardware, we have the operating system, we even have the software. I still don't have my hands on a model. I still maybe don't even know where to get one. So the answer to that question is, of course, Hugging Face. More specifically, it is the Hugging Face Hub, which is basically your one-stop shop for models and data sets and even some really cool interactive applications. As you can see here, this is a screenshot which is highlighting the model that we'll be using today, which is the Llama 3 8 billion instruct variant. It's truly wonderful. As you can see in the sidebar here, the Hugging Face Hub is not purely for large language models. They have models and data sets relevant to, for example, computer vision. Obviously, object detection is huge, that requires a lot of data to work with. So this is a great place to go and get those types of resources and see what other people are doing. Maybe somebody has fine-tuned a model that you want to look at, and more than likely that they would be hosting it here. There's a ton of stuff here. It's awesome. It's really one of those sites, one of those pieces of software. It's a pleasure to use. And graciously, Hugging Face have also developed and now provide the Transformers library, which is it's the meat and potatoes of what's going on under the hood. So the Transformers library is a Python API for whichever your favorite tensor framework is. It's compatible with PyTorch, TensorFlow, and JAX front-end developers. It also provides REST endpoints if you're building some type of application with a large language model backend. And of course, as I just said, going hand in hand with the Hugging Face Hub, it can be used, of course, for natural language processing like we'll be doing today, among other things such as computer vision, audio, and even what's called multimodal models, which is when you might be mixing text and image, or text and video, or text and audio, or audio and video, something along those lines where you're using two different sort of media. So that's where we get model. And I've spoiled it a little bit already, but what model do we choose? Well, you probably, of course, heard of Llama 3. It's one of those models that sort of needs no introduction, but perhaps if you do need to be sold on it, we'll discuss it a little bit here. Llama 3 is an open source model developed and distributed by Meta, of course. Um, it was pre-trained with tons and tons of tokens, more quantitatively 15 trillion, which is quite a lot. They provide two different versions. You can think of it as 8 billion and 7 billion. You can think of these as sort of a low memory version and a high memory version in terms of GPU memory. It has a nice long context length of 80,000 tokens. So you can think of context length roughly as the length of what you're able to pass as a prompt or an input. It scores consistently high on various LLM benchmarks such as MMLU, which is the Massive Multitask Language Understanding benchmark. And if you don't want to take my word for it, you should look at the number of downloads to see how popular it is, because the Llama family on Hugging Face has over 5 million downloads, which is just tons, right? Very popular. So we have all the sort of ingredients here. So maybe if you are very, very quick at installing things, or if you're watching this in the future, you can follow us along on GitHub. Everything that I'll be doing in this live coding example will be available in a repository. So going over to that live coding example, here we are. Again, this Jupyter notebook, I'll be using mainly two Jupyter notebooks today. And all of that entire install process was actually compiled into an install script that will also be available on that repository. So I'm going to go ahead and kick this notebook off. I already have my Conda environment set up, and I'm going ahead and kicking it off because these things can take a little bit of time, of course, to run. And this is just going to be a super, super basic example. So, of course, all we need to import is transformers and torch. That's as basic as we're getting. I'm just doing a basic check here with PyTorch to make sure that nothing is on fire and the hardware is running on what it should be. Today, like I said, we'll mainly be using the MI210. So what I'm doing with CUDA, what I'm doing with PyTorch is just running torch.cuda.get device name. And of course, that's given as the MI210. So you may be wondering if we're running on AMD hardware, why am I using torch.cuda to interact with these things? Shouldn't I be using torch.rockum? Well, the advantage of this is that your PyTorch code can be essentially dragged and dropped between a CUDA device onto a ROCm compatible device. So you don't have to go back through and mark out everything and replace CUDA with ROCm. CUDA you can just think of as being a GPU in this case, as opposed to like a CPU bound PyTorch process. So everything's good. We're running on the correct hardware. I've already downloaded the model and it's available at the path that I've specified here. You don't necessarily have to download your models beforehand. You can specify a generic model name such as Meta Llama / Llama3 8B, and we're using the instruct variant, which is just the more conversational one. It's a little bit more fine-tuned, a little bit more relevant for interacting in this case. So you can provide a generic string like this, and transformers will go ahead and download that model and get things running as they should be, assuming it fits into memory. It is important to note that for the meta models, such as Llama3, you do need to request permission to use them, to download and use them from Meta on the Hugging Face Hub. But in my personal experience, I think I requested permission on for Llama3, and it got back to me, and like I was approved in like 5 minutes max. It's a very fast process, and that's not hard to find. If you just go to the Llama3 page on Hugging Face, then it's right there. It's quite obvious, and then you can get clone it just as you would with any other sort of repository site. So very easy. But if you're Git cloning, again, make sure you have that Git LFS installed. Otherwise, things tend to break. And I also want to note that myself and going on checking on forums and other things, there does seem to be a little bit of an issue downloading with SSH. So I personally recommend downloading Git cloning with HTTPS. It just tends to work better for reasons that I don't really know what's going on under the hood. It just does not break quite as often. So with that covered, we have our model downloaded. We have it specified. Great. These steps. So I'm just setting the device that PyTorch is using to CUDA. And of course, I just have a simple if loop in here. If it's not available, use CPU. But as we'll see, I'll print it out and we'll see, hopefully, that I am indeed using a Torch CUDA device. So the first class that we'll be using from the transformers library is the auto tokenizer class. And that is exactly what it sounds like. You provide it a model. Here, I am just providing it the path to the Llama3B that I've already downloaded. And it basically, it understands the way that Llama3 tokenizes things, right? Because not all models are created equal in terms of tokenization. One model's embedding for the word instinct might be different than another model's embedding for the word instinct. And those types of things. It wants to use the right language to communicate with the model. So we get that set up, and this pipeline class is super, super important. This is the real star of the show in terms of interacting with these things. And this is where, as you can see later on, we'll call this class to actually generate our outputs. But in terms of actually instantiating it, we have a few different parameters here. First off, of course, we're telling it that we want a text generation model because that's what we're doing, keeping it simple, not dealing with any other sort of modality. Passing it the path to the model that is to be used. Of course, that's Llama3. We're setting a precision for it. In this case, we're using floating point 16. These things tend to be on the scale of either floating point 8 or floating point 16, or sometimes even integer. The AI stuff tends to lean on the lower side of precision. And then this is where the accelerate package comes in. So particularly if you're dealing with multiple GPUs, or I would even say even with one GPU, setting device map to auto automatically maps it to the device that we've set up to be that CUDA device that we declared earlier. Even with doing stuff with one GPU, I found it just to be very, very easy and very simple to use. And all it depends on is that accelerate package. So it's basically no cost for just ease of use. But what this line is doing is essentially just assigning that our GPU to be the device to be run on. So finally, of course, we have everything set up. We're getting there inch by inch. Let's give it a prompt. And I would have loved to type it live, but in the interest of time, I wanted to run it beforehand. So I've passed it a prompt here. Let's see if we can get a music recommendation. So I've told it that I like listening to Snarky Puppy and Frank Zappa. What are some other musicians that I might like? And I'll keep you on the edge of your seat for a little bit, because before we find out that music recommendation, we're going to go see exactly how this was generated using the pipeline class. So there's a few different arguments to pass here. Of course, starting with the text inputs, that will be our prompt that we're passing to it. And then we have these two, do sample and top K, which seem a little bit vague. So what do sample does, when set to true, this is the process that we discussed earlier when dealing with the transformer model. So as we said, you provide an input, you provide a prompt, and the model considers this and puts it through the transformer pipeline. And then at the end, we have a vector with relative likelihoods for each token in the model to come next in the sequence. But we may not, well, if we keep it at that stage and we apply the softmax transform to it, then we can just treat it like a probability distribution, right? And then just sample from there. And so that is what do sample when set to true. That is what it does. But we may not want the possible tokens that have a probability of, say, like 0.00001. We don't want to worry about all these smaller ones. So in a reasonable use case, we may say, okay, just give me the sample from the tokens with the top 10 highest probabilities. And that is what top K is doing. We set it to 10 in this probabilistic sequence. Instead of sampling from a distribution over all of the tokens in the model, we're just sampling over the 10 tokens with the highest probability. Or you can more effectively think of it as the 10 most relevant tokens, but there's still a probabilistic process to that. So of course, top K doesn't matter if we set do sample to false. And what setting do sample to false does is we just it applies a technique called greedy selection. So every time it will just choose the token in the sequence that has the highest probability after that softmax transform. So if we think back to our Beatles example, if we apply greedy selection and set do sample to false, then it would just choose Paul every time in that particular example because that was the highest probability. And then these last two are not nearly as complicated. Num-return sequences, we can actually have this pipeline generate multiple responses. You might have seen these if you've interacted with the various online AI chatbots. Sometimes you'll get the which do you like better. So if you want to generate multiple responses, this is how you would do that. And then we're just setting the token ID to the end of sequence token ID to the end of sequence token ID as specified in the tokenizer. So we're just setting it to the ID of that EOT underscore ID that we mentioned earlier. So it knows what the end of the sequence token actually looks like. So finally, let's print our response. As we can see here, this is what I specified earlier. Of course, we're using a CUDA device, so that's good. This is a bit of boilerplate. This isn't actually in the response. This comes from actually instantiating the pipeline. But then finally, here we go. What kind of music should we listen to? Okay, yeah. Snarky Puppy, Frank Zappa. Yep, Snarky Puppy is a great band. Very true. Their unique blend of jazz, rock, and roll music is infectious. If you like them, we might like these people. And I can say, anecdotally, I am quite content with many of these responses. Esperanto Spalling is great. Interestingly, it's interesting running these multiple times because I consistently get, up until now, I consistently got Weather Report and Mahavishnu Orchestra, which are two great bands. But they're not here now, so that's sort of the stochastic nature of these things. And in the spirit of stochasticity of these, it seems perhaps it had a nice opportunity to put an end of sequence token right here, but it did not. And so it kept generating a response. And it gives us some more suggestions, which well, they all seem relevant as well. So that was a subjective question, right? As long as it sort of knew what sort of like jazz or rock musicians were in the world that it was trained on, it could at least spit those out. But how about a little bit more hard factual evidence? So I just asked it to tell me about the company AMD. So maybe if we have some AMD people in the chat, we can see if this is true or if it's completely lying to us about AMD. So it got Advanced Micro Devices, right? Semiconductor company, manufactures microprocessors, GPUs, other semiconductor products. Yeah, I do believe it was founded in 1969, and I do believe they are in Santa Clara. Yeah, main products include CPUs, GPUs, APUs, uh, Epic, which I guess would be a subset of CPU, but not totally incorrect. Okay, and then it's gone on and sort of started generating a response about other companies. This is the nature of doing things live, right? I can do this a million times, and it has this nice sort of succinct response, and then now it's skipping these end of sequence tokens. So AMD is a huge company, right? A long history, tons of documentation, tons of products out in the world. But what about Fluid Numerics? Let's see if it can get anything right about us. So, what can you tell me about Fluid Numerics? It is a company that specializes in the development of numerical methods and software for simulating fluid flow and heat transfer. Reasonably true. Uh, it's sort of speaking broadly about fluid flow, nothing really specific. Yeah, expertise in development of HPC software. Uh, what is the difference between fluid numerics and open foam? That's an interesting one because I'll start on another anecdote here. Uh, Quite often, maybe not every time, but quite often, it would claim that fluid numerics, excuse me, uh, flagship product was open foam, which is definitely not true. But it's interesting that it associates the fluid solving and the HPC stuff with open foam, and so it has this connection at the end here. So those are some interesting examples, I think. So finally, I've been sort of hinting at it this whole time. This softmax transform. What is it actually doing? How does it convert this sort of likelihood vector into an actual probability distribution? So if you recall, uh, when it's trying to predict the next token in the sequence, it generates at the end a vector whose rows are the relative likelihood of all of the tokens in the model. And those relative likelihoods might be extremely large or extremely small or sometimes even negative, depending on what data type you're using. But what the softmax function does, of course, you can't sample that as a probability distribution because the two main things, right, is that uh, for a discrete distribution, the probabilities need to add up to one. Well, I mean, that's true for continuous distributions as well, but the probabilities need to add up to one and the probabilities need to be positive. And neither of those things are necessarily true for this sort of likelihood vector. So what we do here is if each entry in this likelihood vector x is expressed as xi, then we can raise e to that power. Ignoring t for now, we can raise e to that power, and then divide it by the sum of raising e to the power of every element of that vector. And of course, if we think about this a little bit, naturally this does add up to one, because then we would just have the sum over the sum. Of course, that equals one. And raising e to the power of anything is going to strictly be a positive number. So that remains positive. So we also have this extra little t in here. What does this do? This t is temperature. And what temperature does is conceptually, it reduces the confidence of a model in what to predict next. So a higher temperature correlates with sort of less confidence in a model. You can think of it as being a little bit wilder at higher temperatures, and a lower temperature, it is more certain about what token is coming next. And of course, mathematically, we can do a quick thought experiment and verify this. For any value of x, if we raise t to be quite large, the value of x doesn't really matter. This value just sort of tends towards zero. And so for every token, we will tend towards a probability of e to the zero, which is just one. So we'll just tend towards a probability of one over that sum. So as t approaches infinity, we tend towards a uniform distribution for guessing which token is going to come next. And then, of course, in the other direction, as t tends to zero, the larger and more positive values of x are going to dominate drastically. And so when t tends to 0, this actually approaches that greedy selection technique that we saw earlier, because whatever is the most likely is just going to dominate in this sense. And so uh, the key takeaway from all of that is that high temperature equals less certain model, which usually means wilder results, and a lower temperature means a more certain model, so more consistent results is a nice way to look at it. So I have a loop set up here to iterate between some values between 0.1 and 10, and we'll see how temperature can affect these things. I will say before we get into this, Llama 3 does tend to be quite rambly compared to some other models. So even at low temperatures, you can get some interesting results. So let's see what we have. So at 0.1, so each token that it is guessing, it is quite certain that it is what comes next in the sequence. The answer to 2 plus 2 is 4. Okay, it starts off factually. And this is a trend that I've seen playing around with this particular model, is that it tends to repeat things in this sort of patternistic way. The answer to 3 plus 3 is 6, answer to 4 plus 4 is 8. These are all true. Perhaps more information than we requested, but it is succinct, consistent. I assume most of these are true. And so, okay, we start off the same way with a slightly higher temperature of about 0.3. The answer to 2 plus 2 is 4. And then it starts rambling a little bit, I guess. The statement is true, but the way it is phrased is not a question. That is true. We were sort of leading it to finish the sentence. It's a declaration of fact. Okay. This seems, at a cursory glance, it seems to not be getting anything totally incorrect. At least it's coherent, as maybe not relevant as it is. It's at least seems to be speaking English. Likewise for temperature equals 1. So this is the default temperature. The answer to 2 plus 2 is 4. In other words, the answer is 4. The statement 2 plus 2 equals 4 is a mathematical equation, which is a type of statement. Yeah. So again, it is speaking English, but perhaps it's not necessarily relevant, but it's still understandable, which we may see quickly will not be the case with these higher temperatures. So with this one, yeah. So the answer to 2 plus 2 is ... And you know exactly why it will never get a response. Answer, I'll have a cuppa, mate. That's only acceptable reply here. And then it goes off on sort of this nonsense, providing dates and times. This answer should be closed. Perhaps something from Stack Overflow relating to a math question. That might be the line there. I'm not totally certain. And then at extremely high temperature, it gets fairly, let's see here. Yeah, it becomes much less comprehensible. So result, answer to 2 plus 2 is 4, comment by some guy named David in 2014. Yeah, so I think there is no one best method. Answer 5 questions with what and where. What are most ... 1. I think this is ... 2. Answer to 2 1. It's a little bit. It becomes much less comprehensible, and so that is sort of the effective temperature on these types of models. And even in the lower temperature cases, we can see it being a bit rambly. This is a great use case for perhaps fine tuning, which is a whole other deep dive in the large language model world. And so, of course, we ran this one on the MI210. I did want to run another extremely simple script here, just to demonstrate that it is easy to run it on other hardware. I'll go ahead and clear the outputs and run it fresh. So here we're running on an Radeon Pro W7800. It operates functionally exactly the same way, same sort of setup. But what I'm doing here is sampling the vocabulary. And so this is the script that I used to provide the sample tokens at the beginning. And again, we can see this G dot symbol for these tokens. I don't necessarily know what that means, but another underscore perhaps the underscore is used for joining chunks of words together. Interesting symbol here, but yeah, exact same way as we would on the MI210, but run on the Radeon Pro W7800. And so these scripts are available, like I said, on the GitHub repository. There. So as we said, this is a extremely basic introduction to these types of things and these types of models. There is so much more to learn, especially in the realm of techniques such as fine tuning, using maybe going beyond Python, using other techniques. We haven't even gotten into things such as quantization. There is a lot of room to grow, and AMD has some great blog posts. If you don't know about the Rock'em blogs, they are wonderful resources for getting into this stuff. I've used them. I definitely use them in preparing for this. So those are great resources. And of course, you can find Fluid Numerics on the web in all the usual places. Of course, we have our website, which was recently updated, so go check that out. We are on Reddit. Obviously, we're on GitHub. We do put out YouTube videos. We have some cool videos coming up in the coming weeks. And of course, we're on LinkedIn. So naturally, that is the end of the discussion today. Let's move on to the Q&A and see what kind of interesting questions we have. And Joe will be joining me for the Q&A. So maybe I can take a drink.
Yeah, take a drink of water. That was great stuff, man. Yeah, I got a few here in the chat already, Garrett. I'll go ahead and throw some your way here. And then, so the first one is, I'm confused. Are the AMD devices CUDA devices? Can I talk PTX to them? You want to take that one?
So PyTorch thinks of them as CUDA devices, but I'm not certain if you could necessarily talk PTX to them.
Well, yeah. So, and I think I'll add the clarifier there that the PyTorch developers left the naming convention just because that's what people did, and they didn't want people to have to rewrite their code, right?
So yeah, it's totally ease of use.
If you guys were like paying very close attention, there was like some of the slides where you're showing the pip install, PyTorch, Torch Vision, Torch Audio stuff. There was a link to change the index URL to the Rock'em builds of PyTorch. Basically, if you want to run on AMD GPUs, you just point to those indexes. If you want to run on NVIDIA GPUs, you just use the NVIDIA indexes for installing PyTorch. That's really the only functional difference, but your code can stay the same. So like if you install with the Rock'em backend, no, it's not going to talk PTX. It's going to be the AMD GCN HSA. But yeah, you don't need to change your code. You just need to change the package you install as a dependency to be able to use AMD GPUs. All right, we got one of them. Well, we got two, but like they look like the same thing. And maybe you answered this in the last slide here, but it says, can you share references to docs or repositories about running a training job in parallel on multiple Radeon GPUs, not Instinct? And like they're thinking of a case where they have a model with that needs more than 48 gigs of GPU memory.
Off the top of my head, I'm not certain if the Rock'em blogs do have a multi-Radeon, a walkthrough specifically for multi-Radeon, a multi-Radeon setup. But I would recommend looking at the Rock'em blogs. They probably have the relevant information.
I think
in parallel stuff.
Yeah, Rock'em blogs definitely would be a place to go. Hugging Face does have a few things. I mean, they tend to be like, so far, I think the documentation's catching up. They're NVIDIA specific, but there's a package called Accelerate. And maybe one of the backstage folks can drop the links for this, but I sent over some Hugging Face pages. There's one for training and one for inference, but you can use the Accelerate package to set up a distributed environment, and you can have everything kind of handled in the background by the Accelerate package. That would be the way to go. There's spots in those docs where they reference like export CUDA visible devices equals whatever. If you're on a system that has like a job scheduler, it's likely device selection would be handled for you via Slurm or PBS. But if you're doing this like course on your workstation and you just want to use all of them, you could just set I think it's HIP visible devices rather than CUDA visible devices. And just set it to if you have 4 of them, for example, just HIP visible devices equals 0, 1, 2, 3, and you'll be good. I hope that answers the question there. If nothing else is coming in, if you guys want to drop any more questions, we'll hang here for just a minute. If not, we'll go ahead and wrap this up, I guess, shortly. I don't know. What do you think, Garrett? Should we call it?
I'm good to call it.
Well, thanks everyone for tuning in. It's great chatting with you all today. See you at the next one.
Yep. Thank you so much.